We have a table here that gives a person's balance every couple of years, and what we want to do is build an exponential model for this data. Now, since our inputs are equally spaced, to see if it's exponential, all we got to do is check the ratio of outputs. So 112 over 100, which is 1.12, 125.44 over 112. And so what I'm doing is all I'm doing is this divided by this divided by this, so on and so forth. So we're going to bring in the calculator here, but we won't do all of these for time's sake. You'll kind of see the pattern. 140.49 over 125.44. That's enough for this particular problem. What we would do in general is check all of them, but I just want to demonstrate. So we would do 125.44 divided by 112. Once again, we get the 1.12, so we're starting to see a common ratio. 140.49 divided by 125.44. Yeah, it's not quite 1.12, but it's close enough. If we were to round to 2 decimal points, it'd be 1.12. So what we're seeing is that this account's growing by 12% every 2 years. So we can think of this as the 2-year growth factor. So if we wanted to build a model for this just with what we have, and we're going to use t equals 0 corresponding, not 1998, but to the year 2000 to correspond with this data. Sorry about that. Well, $100 is in there initially, so the balance is going to be 100. I'm going to show you a couple different ways to think about this. I'm just going to use the 1.12, but remember that this is a 2-year growth factor. So it's grown by 12% every 2 years. So I need to compensate for that. So I'm not just going to raise it to the t, I'm going to raise it to the t over 2, because that's going to allow me to go in 2-year groups. So 12% is not the annual growth rate. If we wanted the annual growth rate, what we'd have to look at is the 1-year growth factor, which, if I were to rewrite this, I would take out the 1.12, I'd raise it to the 1/2 first, and then to the t, which makes this our annual growth factor. So if we wanted the annual growth rate, which we didn't need to in this one, but I just want to show you, it's good practice. We would take that annual growth factor, which is the 1.12, and we'd raise it to the 1/2, or take the square root. So this was the 2-year growth factor. Here's the annual growth factor. So the annual growth rate, this is basically like finding effective yield. We have an annual growth rate of about 5.83% for this account. But all we needed was our model, which we have. And now, that should say $900, not $9,000. Excuse me. If we wanted the balance in 2016, we have our model. And all we're going to do is we're going to put the appropriate t value in. Well, 0 corresponded to 2000, so 16 would correspond to 2016. So 1.12 to the 16 over 2, or to the 8. That's something we can calculate very easily. 100 and then the 1.12 raised to the 16 over 2, or this one again we can just put in as 8. So there's our balance. We'll round it to 2 decimal places because we're dealing with money. So 247 point, well, let's do this, 247.596. So our answer, because we want our units, would be $247.60 would be our balance. Lastly, when will this person's account reach $900? And I'm going to show you how to do this with the calculator in this particular case. So we're going to set our account 100 times 1.12 to the t over 2. Again, remember that we divided by 2 because ours was a 2-year growth factor. If these had been 3-year gaps, we would have divided by 3. If they would have been 1-year gaps, we would have divided by 1 or not written it at all. equals 900. And so right now I'm going to just show you how to do this with a calculator. This can be done with logs, but for this particular problem, we're not going to use logs. So what we're going to do is we're going to put in our model on one line, so 100. If you want to divide both sides by 100 to make the numbers a little bit smaller, there's nothing wrong with that. Completely understandable. And we'll use x over 2. So there's our model, and then we'll put 900 on the second line, and what we're going to be looking for is where they intersect. But we need to make sure we have a window that will allow us to see that. We know it's going to take more than 16 years to get up to $900, so let's start with 40 for years, and let's make a y max needs to be bigger than 900 so we can see it. So let's make the y max 1,000. So we'll graph. Here comes our exponential function first. Again, we're looking for where they intersect, and we may have to adjust our window a little bit. Looks like we're going to see our intersection, so there's our answer right there. So we do second, calculate, intersect, enter, 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 and there's our intersection. So it's going to take about 38.77 years after 2000. So according to our model, this will happen in about the year 2038. So now, one thing we could do also have done for this one, and I just want to show it to you real quick, because we have this table of data, we could have done exponential regression. So just a quick little review on exponential regression stat. You're going to edit your lists. I already have it in there. So I put my inputs in L1, outputs in L2, and always use just the last digit or 2 digits of the year, otherwise you're going to get an overload. And then we'll go to calculate our exponential regression, and we'll see how this thing lines up. Notice our R is really close to 1, so this data is almost perfectly exponential. Our A is right around 100, which is what we found. And then look at what it gives us for a B, the 1.58297787. Well, if you remember before, we found the annual growth rate, or the APR, to be about 5.83%. Well, there's our 5.83% right there. Because this is doing an annual growth factor, we did ours as a 2-year growth factor just to make the numbers easier.